All right, tonight we're going to be talking about where does the energy go during a thermic change, such as exo and endothermic processes. During an exothermic reaction, heat is released into the surroundings. So if I were to look at a diagram that's found in most chemistry books, what I would notice is that the reactants, or the energy that's stored in the reactants, is higher than the energy that's stored in the products. And this difference right here in energy is the heat that is released during the reaction. If I were to translate it back into the LOL charts from previous units, what I would notice if I were to translate this diagram into an LOL chart, it says that my chemical energy was high and then it went down. Okay, so it went high to low. This is where that transfers from that to that. And then what we notice is that this difference is the heat energy that's lost. So this would be, remember if we remember Q is heat. So this is what we would be able to measure, is that heat loss of this exothermic reaction. All right, so here's an exothermic reaction that occurs, and it's a combustion reaction. How do you know? Because you have that hydrocarbon plus the oxygen, and you're producing carbon dioxide and water. So if we wanted to worry about energy, what we would want to ask ourselves is, where would the energy go? And if you think about an exothermic reaction, exothermic means that the energy was released by the reactants, so the energy would be energy would be a product. Why? Because this energy, if we looked at our LOL, was higher than this energy. So if energy is like mass, which it is, and it needs to be conserved, so whatever energy we start with, we need to end with. If this has a larger amount of energy in your reactants than in your products, then somehow in order for them to balance out as far as energy goes, we need some more energy in the product side. So for exothermic reactions, energy is written on the product side. It also makes sense when you think about exothermic. The heat that is released, we tend to think of it as a product of the reaction that went on. Okay, so if we reacted these guys back to the methane, if we reacted these guys, we would notice that it would be hot. Think of combustion reactions. You see flames, you see heat. So it would make sense that we would think of heat being on the product side. And what is heat? Well, heat is just a form of energy. All right, endothermic reactions, on the other hand, is where heat is absorbed by the system. So what would end up happening is that the surroundings actually feel colder. Now, if I were to look at any energy diagram in a book, what I would notice is that the reactants, if I were just looking at the energy that's stored in the reactants and the energy that's stored in the products, the energy in the reactants would be less than those of the products for an endothermic reaction. If I were to try to translate this diagram into an LOL chart, okay, that's the energy difference, I would notice that my reactant of chemical energy was here, and then it went to my products, which is an increase in chemical energy. And once again, this is for endothermic, so it's absorbing that energy. And this energy difference is right here. And we do it in the form of heat. Whatever we are measuring, we only measure in the form of heat. So whatever's in this O is always going to be the measurement of heat, because this is what we can measure. Okay, we can't necessarily measure easily the energy that's associated with a particular compound, but we can measure how much heat is transferred or gained or lost as far as temperatures go. Now, what I do want you to note is, just like before with our LOL diagrams, whatever we gain, that is what we need to relay. Okay, so notice that we started with 2 bars here. We added 2 more bars, so we're going to go up to 4 bars total. All right, so here's an example of an endothermic reaction. So if I looked at this endothermic reaction, basically I have calcium carbonate, and it's decomposing because I have a compound producing 2 new compounds. So I have one thing going to 2. And what I noticed is that it's an endothermic reaction, so it felt cold to me. Okay, so where would the energy go? Well, if you go back to your energy diagram, we know that there's energy for our reactants and it went up to our energy for our products. So how do we get this? Well, we need to be able to add energy to it. So where would the energy be? Well, this transfer is the energy that's being gained for the calcium carbonate to undergo that reaction so that we can get up to this amount of energy that's stored in the products. Okay, so for endothermic, which would make sense, it's written on the exact opposite side as for the exothermic reactions. All right, so how does heating the reactants result in an increase of chemical energy, or ECH? Well, first, it's really important for a person to understand what is a change in chemical energy regardless, and why does it occur? Well, it occurs when you rearrange the atoms. And how does this rearrangement occur? Well, it comes from collisions of molecules. Okay, so by colliding different molecules, you'll break or make bonds and therefore rearrange the atoms. Low energy collisions, meaning that they are not going very fast typically, are unlikely to produce any molecular rearrangements. And that makes sense. If you think about somebody like in football who weighs 100 pounds and they're trying to change the position of somebody who weighs, like, say, 350 pounds, they're not going to do as much as if it was a 350-pound person going against a 100-pound person. So by heating up these particles, what you can do is you're going to make these guys go faster. So they have more and more speed so they can do more and more damage. So now by these particles running into each other, they have enough momentum or energy in order for the reaction to occur. So what I'm going to do now is I'm going to go over how do you break down the endothermic reaction. So for an endothermic reaction, remember you're heating up that energy. Okay, so what happens is you're going to go for the thermal energy. It is going to absorb energy in the form of heat. How is heat gained or lost? Well, it's always going to go towards your temperature. So I go from 2 bars and I'm going to add 2 bars of energy in the form of heat, which is temperature. So I'm going to go up to 4 bars for my thermal energy. All right, so what then happens though is that the temperature always wants to maintain that of the environment. So even though it absorbed that energy, it wants to go back to normal, okay, which would be the 2 bars that I originally saw, because everybody always wants to be around the same temperature as its surroundings. So what it's going to want to do is it's going to want to transfer that thermal energy into a different type of energy. And what it does during an endothermic reaction is it donates that energy to your chemical energy. So it's able to rearrange those bonds. When it does that rearrangement, what happens is that it's going to donate those 2 bars. And so now my chemical energy went up to 4 and my thermal energy went back to the original, which is 2. You always want to end for these LOL diagrams to go back to the same amount of temperature or the original temperature or energy associated with that temperature. Okay, so here's an overall LOLOL diagram. Okay, notice that we have an L, an O, an L, an O, and an L. So that's where we get LOLOL. So first, for an endothermic reaction, what you're going to be doing is you're going to be adding energy. Okay, so it's going to absorb that energy. Anytime you are dealing with the O's, you are going to be adding or taking away from your thermal energy. It's always going to go towards your ETH. Okay, go towards or taken away from your ETH. So now I added 2 bars, so that's why I went from 2 bars to 4 bars here. Okay, but once again, everything temperature-wise wants to go back to what it originally was, which would be 2 bars. But you can't get rid of energy once you have it. Okay, because energy is always conserved. So what ends up happening is it's going to donate those 2 bars to your chemical energy. So therefore now instead of having 2 bars in your chemical energy, you now have 4 and your ETH went back to what it was originally, so it's extremely happy. All right, so now if I look back to my ECH curve for an endothermic reaction, what I notice is that it went from here, okay, I'm looking way at the bottom, to up here, which makes sense as if I look at my ECH, which is this type of a diagram, I went from 2, and by the end of the reaction, I went up to 4. Okay, so notice how this diagram looks very similar to that line. So it goes up in chemical energy. So once again, these diagrams down here are the energy that's stored in the chemicals. All right, so how does heating the reactants result in a decrease of chemical energy? So what happens with that one is you have ECH, which is, once again, how do you change your ECH? It's due to the rearrangement of atoms, either going more or less energy. And how do you do that? You do it by the collisions of the molecules. So when you have a reactant of molecules that collide to produce products that store less energy, new molecules will move more rapidly away. So they'll go from higher chemical energy to lower, which means that they now will have more speed. So let's look at the LOL to try to explain this. All right, so this is for exothermic reactions. So what happens is that during the collisions, these chemical energy, remember we're going from a high chemical energy to a low chemical energy. So we're going to go donate that chemical energy to ETH. I do want you to note that we will never be dealing with it during this unit, your EPH, ever. Okay, so your EPH will always remain 0. Okay, so during an exothermic reaction, what happens is that your chemicals, your original chemicals, go from a high energy substance into a lower energy substance. Okay, so if I look at that, I go from a high energy from here and I go down to a lower energy. How does it do that? Well, it donates the energy into your thermic one, so meaning that they will then go faster. Okay, so what happens is you transfer 2 of your chemical energy, which is associated with the bonds. You are going from a higher energy to a lower energy as far as the energy stored in the bonds. And so now where is it going to go? It's going to make your particles go faster. Okay, so now that the particles are going faster, remember everybody wants to be thermally at what they were originally, because you always want your system and your surroundings to be about the same temperature, and that's why heat is always transferred to and from, so that they reach that equilibrium with one another. But what happened is that chemical energy forced that ETH to go up. Well, it doesn't like that, so what it's going to do, it's going to release that new energy that it received in the form of heat. Remember, anytime you are dealing with your O's, you are dealing with changing your ETH. So now that I lost my 2 bars for my ETH, I have now gone down to my original ETH of 2 bars. All right, to look at an overall LOLOL diagram, okay, so what happened during an exothermic reaction? Number 1, your chemical energy is transferred. It goes from high to low. How does it do that? It donates 2 of its bars to your thermal energy. Okay, so now your thermal energy is unhappy because it went from 2, which is what the surroundings is, to 4. So now it's hotter than the surroundings. So what is it going to do? It's going to try to release those 2 bars, okay, so that it can go back to its original. So I started with 2 and I need to end with those 2. Okay, so now when I look at my ECH curve, what ends up happening is that I go from 4 down to 2 because I have more energy stored in the original, and then now I'm releasing that energy that's stored in that chemical into the thermal form. So looking at my diagram, I start with a high reactant. Looking at that, and it translates to a lower product. So this diagram, once again, on the bottom is typically what you see energy diagrams for exothermic, but we are translating it into an LOL diagram to show how those collisions actually result in a lower amount of energy stored in the products. All right, hope you have a basic understanding of LOLOL diagrams. I do want to note for this class, every time you have an exothermic reaction, they will always be the exact same LOLOL diagrams And every time you have an endothermic reaction, you will always be producing the exact same LOLOL diagrams. So once you're really comfortable with one endothermic, you pretty much are comfortable with all endothermic reactions for this particular class. And same thing with exothermic. Once you are fine with one exothermic, you are basically fine with all exothermic reactions.